when you are in the Himalaya and when you go to those serene places below the snow peaks. This is lifetime dream to be there. It's so wonderful to be there. Unless you are there, you'll never realize what you are missing.
This is the legendary Himalaya, a magical land of geological extremes. These are the world's youngest and tallest mountains, and still growing. The Great Himalayan Range has grown so high that it has altered the world's climate. It created the Indian monsoon, which rains down on the mountains, eroding them and forming rivers, some of the Earth's largest and most powerful. Rushing from the mountains, the Himalayan rivers carry the greatest sediment load in the world and deposit it to make the planet's largest river deltas. The land nourished by these rivers is so rich and fertile that it supports the Earth's greatest concentration of people. But many of those people are also deeply affected by the Himalayas' extreme geology. Huge landslides and frequent flooding shape and reshape the landscape. And deep beneath the land, a grand geologic drama is unfolding, of great interest to scientists. Two gigantic tectonic plates are clashing in the hot depths below, creating unexpected, far-reaching danger, much of it unknown to science until now. A vivid display of the brute geologic force that pushed up the Himalaya was unleashed in Nepal in 2015. The Gorkha earthquake marked a turning point scientifically. More than any previous Himalayan earthquake, this one had been much anticipated by Earth scientists, including Nepali geologist Bishal Upreti. Before it struck, Bishal and his colleagues had pieced together what the earthquake proved was an accurate geologic picture of the region. Clearly visible from space, the Himalaya marks the spot on the globe where the enormous Indian tectonic plate is slowly diving beneath Asia. When parts of the two plates get stuck or locked, as they often do, stress builds up on the plain between them. Eventually, the stuck places are freed in a major earthquake.
The Himalaya is considered to be one of the most seismically active parts on Earth. Many other places like Indonesia or Japan, or there are many other parts of the world where we have a lot of earthquakes, but Himalaya is one of them, very active seismically. And in history, if we go back, we have a lot of very large earthquakes killing a lot of people. We are very much concerned about big earthquakes.
For a number of years before the Gorkha earthquake, Bishal and other earth scientists had been predicting a major earthquake centered in Nepal. But no one was able to say exactly when it would strike. The Earth doesn't behave like clockwork, and earthquake prediction is still a crude business.
Earthquake scientists cannot yet provide predictions a few hours or a few days ahead of an earthquake. But what we can do is tell the public when to expect earthquakes over the 10-year, 20-year time frame.
That's what geologists did in the years leading up to the Gorkha earthquake in Nepal. But preparations were minimal. Few buildings were constructed with earthquakes in mind, and centuries-old temples and palaces were weakened by age.
The quake hit about noon on a Saturday.
The Gorkha earthquake was deadly, killing more than 9,000 people. But it yielded a trove of scientific data. Since the earthquake, new insights have sharpened predictions of where and when future earthquakes will strike the region. The reach of the seismic threat encompasses all of the Himalayan nations and emanates mainly from one great earthquake fault. The edge of the fault can be seen on land, where it runs south of the tall peaks, from Pakistan through India, Nepal, and Bhutan. This is the main Himalayan thrust fault, known for its history of destructive earthquakes. It is so large that geologists call it a megathrust. Megathrusts are notorious for generating extremely large earthquakes. One of them, a magnitude 8.8, struck Chile in September 2015, causing a tsunami. Megathrust earthquakes often happen in subduction zones underwater, where an oceanic plate dives beneath a continental plate, like the magnitude 9 Tohoku earthquake of 2011 and the resulting tsunami off the coast of Japan. But the megathrust below the Himalaya is not underwater. This can make it easier to study geologic features, such as earthquake faults, where they can actually be seen. And on land, it's easier to set up GPS instruments to track the moving tectonic plates.
As we build up a record of where earthquakes happen, we get a sense of how frequently earthquakes recur on particular plate boundaries. And because we have the GPS monitoring to tell us how fast the plates moving towards each other or past each other, we can look at how big these earthquakes are, characteristically in one place, hence how many need to happen, how often, to take up this plate motion.
Geologists have calculated that the Indian plate is pushing relentlessly into Asia, moving northeast at an average of 5 centimeters or 2 inches per year. But the front of the Indian plate lurches forward unevenly. On some of the segments of the main Himalayan thrust fault, the historical record reveals that no large earthquake has occurred for centuries. These are called seismic gaps. In these segments, the fault is locked and stress has been building for a long time.
We can look at the places where earthquakes have happened along the Himalaya, and we can find places where earthquakes haven't happened for hundreds of years now. And those are the places that are dangerous. Those are the places where large earthquakes are waiting to happen.
One of the most worrisome seismic gaps is in western Nepal. About 200 kilometers west of Kathmandu is the busy tourist town of Pokhara, the second largest city in Nepal. It's the gateway to the Annapurna Range and the Annapurna Circuit, a popular trekking route among international visitors. This segment of the main Himalayan thrust fault is locked and dangerous.
In the last 500 years, in the western part, we don't have such a major earthquake. Therefore, there must have a lot of energy stored in that part of Nepal.
Danda Adhikari is a geologist at Tribhuvan University. Like his colleague Bishalu Preti, he worries that this locked part of the fault could break at any time, with serious consequences for the people of Pokhara. The last megaquake struck here in 1505, and stress has built up ever since, enough to produce a magnitude 8 or even higher megaquake. Farther to the west, another seismic gap, quiet for 450 years, spans Jammu and Kashmir. It is next to where a massive temblor struck in 2005. That one, the magnitude 7.6 Kashmir earthquake, killed 86,000 people across Pakistan and India. To the east, there's yet another dangerous locked segment on the main Himalayan thrust fault. This one has not yet received the world's attention, but it is directly beneath the kingdom of Bhutan. Tucked between India and Tibet, Bhutan has historically been isolated from the rest of the world. Now that its borders are slowly opening to tourism, visitors are discovering its treasures, both natural and artistic. Steep trails through wooded mountainsides lead pilgrims and tourists alike to Buddhist monasteries, fortresses, and temples hidden from the eyes of the outside world until recent decades. Traditionally decorated houses and shops grace both cities and countryside. But many of Bhutan's buildings are made using a traditional rammed earth method, in which walls are built from dirt, packed hard into wooden forms. Scientists fear that they may not hold up in a major earthquake. Bhutan has not been directly hit by a major earthquake in 300 years. Beneath this Himalayan nation, the main Himalayan thrust fault is locked, constituting another seismic gap. Recent studies show that stress is indeed building on the locked fault, making a future large earthquake likely. Will Bhutan be ready when that earthquake strikes? And what about to the north? After all, the Indian plate is drifting mostly northward to collide with Asia. Is there danger in that direction as well? This is an important question for the people of Tibet. Stretching 1,000 kilometers north from the Himalaya, the Tibetan Plateau in China is the world's largest and highest plateau. Its average height is more than 4,000 meters.
To the north of the Himalaya, Tibet was uplifted. It was so enormous in terms of its area, in terms of its height.
As it rose up with the Himalaya, beginning 50 million years ago, the effect was felt worldwide.
When you have very large part of the earth is uplifted, that changes the entire global air circulation system. Then all that makes the global climate change.
The colliding Indian and Asian plates not only pushed up this huge climate-changing plateau, they also riddled it with active faults. Over the years, Tibet has been rocked by many large earthquakes. Yet the tectonic forces that produce those quakes are not well understood. In fact, scientists have not yet figured out how the colliding plates are positioned below. There is evidence that the leading edge of the Indian plate lies somewhere under Tibet, but no one knows exactly where.
So they said the road is okay.
At the forefront of the quest to find out is geophysicist Simon Klemperer,
East, north.
who, like Bishalu Preti, is a long-time Himalayan researcher. Simon has worked in Tibet for 25 years.
Tibet, where India and Asia, two separate tectonic plates, are colliding, the boundary zone is not a sharp line, it's a broad plateau nearly 1,000 kilometers across. And trying to explain how that broad crush zone evolves, that's the challenge for us today. Let's get the probe out, because I bet that's hotter coming out of the source.
Because the plateau is so large and remote, Simon devised a novel way to find the Indian plate below. He led a team of American and Chinese scientists on an expedition in search of hot springs. When they found them, they took samples of the water and gases bubbling up in the pools. The hot springs bring up traces of elements from the depths. The element of greatest interest is helium. The ratio of two different isotopes of helium in the gases can reveal how far down the roots of the hot springs go.
We'll probably do the water sampling at the outlet down there and do the gas sampling right here.
The hot water can come from surprisingly deep in the earth. Geologist Carmen Wynn has sampled hot springs on several continents.
The chemistry can tell you a lot about the source of the water. So if the water is very, very clean, it's probably sourced from rainfall. Some of the fluids in hot springs can come from very, very deep, like deep as in the mantle. In the Tibetan Plateau, that means possibly 70 kilometers or more.
The Earth's mantle lies below the tectonic plates that make up Earth's outermost layer, the crust. If a hot spring contains fluids that are coming from the crust, the spring could be over either the Indian plate or the Asian plate. But if a hot spring's fluids are coming from the mantle, that means it is north of the end of the Indian plate.
Okay, so I'm going to close this off now.
By sampling lots of hot springs across Tibet, the scientists could make a map of where the Indian plate ends. That would bring a much better understanding of the seismic hazards confronting people all across the region. And seismically, Tibet might not be the end of the road.
First, we'll go south.
Some scientists suspected that the danger from the colliding Indian and Asian plates reached even beyond Tibet. That possibility took geologists farther north still, 2,000 kilometers north of the Himalayan mountains, into Mongolia. Much of Mongolia consists of grassy pasture lands. People here are nomadic and live in movable houses called gers. A traveler might come across one human structure on the landscape as far as the eye can see. It's hard to believe that Mongolia is connected in any way to the far distant Himalaya. But some geologists believe that it could be.
The greens are country roads and the yellows are local roads.
This and other geologic mysteries brought geologist Carl Wegman on a scientific expedition to a remote upland part of Mongolia. It was not easy to work here, but Carl welcomed the challenge.
This is my 6th trip to Mongolia. And the thing I really like about Mongolia is that there's no fences, there's very few telephone poles, very few roads, it's just open space. And you just get that sense of sort of vastness and open landscapes that don't exist in Europe or North America. Mongolia is the least populated country on Earth, so there's people distributed across the landscape because they're nomadic, so you always see people, but the density of other human beings is incredibly low, and there's just this sense of openness.
Not much has changed across this landscape since the time of Genghis Khan's rule in Mongolia and beyond.
The horse armies of the Mongolian Empire back 800 years ago formed in this part of Mongolia.
One geologic mystery confronting Carl's expedition was that the land had been raised thousands of meters above sea level, unusual for the middle of a continent.
1,000 feet above sea level. That's sort of the normal for the middle of a continent. Here we're at 8,000 feet and the mountains go up to 15,000 feet.
One theory connected Mongolia with the Himalaya. In this theory, the distant collision of India and Asia below the Himalaya piled up the Earth's crust far out in front of it, like a bulldozer, elevating Mongolia's terrain. But this idea did not fit conventional plate tectonics theory.
Could you ask him what is the name of this mountain?
The plate collision was too far away.
Here. So I saw a few more sticking out of the ground here.
Geochemists Rick Carlson and Dmitry Ionov looked for answers on the flanks of Mongolia's dormant volcanoes.
Plate tectonics solved a lot of things in geology, but it predicts that in the middle of a plate it should be a nice stable area, nothing exciting's happening. But here we're sitting in the middle of Asia and we're up at over 2,000 meters. We have all this faulting making these mountains here. So this doesn't fit plate tectonic theory.
I think we need to take a closer look at this.
Something geologically very active is happening here.
There was another geologic anomaly in Mongolia. 3 earthquakes, greater than magnitude 8, had struck in the past century. What triggered these huge earthquakes, which are so unusual for the middle of a continent? There was one intriguing possibility. Scientists had measured stress in the Earth's crust, originating at the Indian-Asian plate collision below the Himalaya. Could that stress be what set off the earthquakes here? The big earthquakes that rattle Mongolia are a concern in Mongolia's capital, Ulaanbaatar. Over 1 million people live here, more than a third of the country's population, and buildings are not earthquake resistant. If Carl's research found that Mongolia's geology was influenced by the plates colliding far away below the Himalaya, that would confirm the extreme power of that collision.
Okay, I'll get you another load.
Plate tectonics theory itself might need a major update. Chemical analysis and age dating was done of rocks collected from Mongolia's volcanoes. The results showed that the uplift of Mongolia was not caused by the faraway collision of India and Asia. Instead, the high terrain is probably the eroded remnants of a great mountain range that existed here long ago. But a Himalayan connection to Mongolia still stands. It's when faults in Mongolia's rock formations rupture in big earthquakes.
Movement along those faults seems to be triggered by the propagation of stress through the Earth's crust from the collision of India and Asia.
This stress began building millions of years ago, after the Indian and Asian plates collided far to the south.
It's like a shock wave that's been slowly propagating northward through the crust of Asia.
Those Mongolian earthquakes are exclamation points on the extreme power and reach of the plate collision below the Himalaya.
Each of those 8 measurements gets one line. So we probably
Meanwhile, new research had started to the south of the Himalaya. Scientists working there were about to discover that the power of the colliding plates and the danger extended in that direction as well, with potentially much greater effects. Just east of Bhutan, the main Himalayan thrust fault rounds a steep bend and becomes a subduction zone called the Burma Arc. The Burma Arc marks the collision of the Indian and Asian plates as the boundary between them runs south from the Himalaya. Sitting on top of the Burma Arc is one of the most densely populated countries on Earth, Bangladesh. Until recently, very little was understood about the geology of this flat, wet land, home to the world's largest river delta. Historic records show that there have been huge earthquakes in Bangladesh, but these happened long ago, and today no one remembers them. Most buildings are not constructed to withstand big earthquakes, and people are not prepared. This exposes the population to great danger. So scientists scrambled to identify where the most dangerous faults lie. Structural geologist Humayun Akhtar of Dhaka University was at the forefront of this effort.
Our cities are not built in a planned way, and this cannot be changed in few years also. So we have to cope with this system, and we have to educate our people how to cope with the earthquake. We are working for that, how to educate the people during an earthquake, how they will respond, how they will take shelter.
Humayun's group had grown through the years to include scientists and students from around the world. They started by installing a network of seismometers to map the earthquake faults. scientists also installed GPS instruments to get an overall sense of the plates moving below in real time.
Yeah, the north and eastern part of Bangladesh.
If you want to measure how fast the plates move, geodesy is the gold standard. GPS, the global positioning system, the same instruments that we use not to get lost in the backcountry, a higher quality of those instruments and the same satellites are what we use to measure the plate motions.
One GPS antenna was mounted on the roof of the geology building at Dhaka University. It was an old one, established in Bangladesh in 2003.
Let's go and check the data.
But it still worked.
Okay.
As Humayun and his colleagues investigated, they sensed they were onto something that could be the source of the mysterious large earthquakes of the past. But they did not yet know precisely where or how big this geologic structure was.
There literally is probably centimeters of finer material.
Meanwhile, a group of earth scientists, led by sedimentary geologist Stephen Goodbread, had begun to study the surface of Bangladesh.
I think tomorrow will be the test.
Steve had been working in Bangladesh for many years.
I grew up on the east coast near Chesapeake Bay, and I've always loved the water, the interface between the land and the ocean. And there's no more exciting place in the world to study. And there's no place that the science matters more than in a place such as Bangladesh.
Understanding the land's surface was crucial. The surface is where people are directly affected by Earth's natural forces. Some, like earthquakes, generated deep below. But for the scientists, this dynamic landscape was not easy to figure out. A lot of unusual things seemed to be happening in the area. It started to look as though the landscape, and even the gigantic rivers flowing through Bangladesh, might have been modified by huge earthquakes of the past. But Steve and his group soon realized that another major force, coming from above, strongly influenced everything that happened at the surface here. The Indian monsoon. The monsoon was created by the rise of the Himalaya and Tibet. Before that, there was no monsoon. But gradually, the rising terrain blocked warm, moist air coming from the Indian Ocean and caused it to fall as rain. Each year, the relentless rains of the monsoon swell the powerful rivers pouring from the Himalaya. These rivers accomplish something truly phenomenal. They bring down enough life-sustaining water and sediment to create the most productive swath of fertile land on Earth, rich enough to feed a huge number of people, from Pakistan to China.
If we take all of the areas of South and East Asia that are fed by the rivers coming off the Himalayas, they account for 45% of the Earth's population, 45% of 7 billion people. And the area of land that these countries encompass is only about 11%.
That's about 1/10 of the world's land, supporting almost half of the world's people. But the great riches of this land come with a price. Of the world's 10 deadliest natural disasters in recorded history, 8 have occurred in this region. It is within this geologically turbulent and fertile region nourished by the Himalaya that Bangladesh lies. Because of the monsoon, Bangladesh is one of the wettest countries on Earth. Most of Bangladesh is flat and lies less than 10 meters above sea level. Some years when the monsoon comes, as much as 2/3 of this nation is underwater. Somewhere below the placid, watery surface, powerful, but as yet unknown, forces were lurking. Those forces, and their potentially deadly interaction with the land and rivers above, caught the attention of another scientist, geophysicist Mike Steckler.
So
These are all bricks, no?
yeah, these are all bricks piled up. Yeah.
Like Steve Goodbread, Mike was drawn to complicated geologic puzzles.
It just shifts it.
He too became intrigued with Bangladesh.
Bangladesh is a really fascinating country because there are a lot of different things that are happening here. We have the Ganges-Brahmaputra Delta, which is formed by those two rivers that take most of the sediments from the Himalayas and bring it down and build the world's largest delta. At the same time, there are two major plate tectonic boundaries that are colliding with that delta.
The building of Earth's largest delta starts in the high Himalaya of Nepal, in the headwaters of the legendary Ganges River. In northern India, the Ganges flows through the ancient city of Varanasi. Here, Hindu pilgrims come, as they have for thousands of years, to perform ancient rituals in these waters, which are considered sacred. From Varanasi, the Ganges flows east and crosses into Bangladesh, where it merges with another giant Himalayan river, the Brahmaputra, which originates in Tibet. Together, the rivers create the Ganges-Brahmaputra Delta on the Bay of Bengal.
The entire delta is built from a huge amount of sediment that has been eroded from the Himalayan mountains, and it's deposited in this area.
Scientists have calculated that more than 1 billion tons of sediment arrives here every year. It's an astonishing 8% of the world's total sediment supply, all coming into one country, Bangladesh. It replenishes the soil, keeping this area extraordinarily fertile. The sediments, though, posed a special challenge to the geologists.
One of the impacts of the sediments is that the major faults here that give us the largest risk for an earthquake are buried underneath the sediments of the delta.
I mean, there's no valley. It's like looks
Building up over time, the delta sediments had become very thick. In places, they were more than 10 miles thick. That's kilometers of sand and mud covering up the earthquake faults that might otherwise be seen on the Earth's surface. Suspecting this giant sediment pile and the water that carries it was a geologic force in and of itself, the scientists drilled wells and installed sensors to find out. Sure enough, it was a geologic force. The sediment and water actually weighed down the land. For the first time, the scientists measured a 5-centimeter or 2-inch drop in the Earth's crust during the monsoon. Sedimentologist Carol Wilson was studying how the people of Bangladesh dealt with these extreme recurring shifts in their landscape.
They've learned to live in this land that constantly is flooded by the monsoon every summer, and then also they have the added effect of tropical storms that could flood the coastal areas as well.
In fact, living with the temperamental character of the delta's waterways is something that people have been doing for thousands of years. But a new watery threat brought on by global climate change may challenge people as never before.
One of the concerns in the coastal landscape of Bangladesh is that projections of sea level rise lead to the idea that much of this would be flooded in the next century and that tens of millions of people would be displaced from this landscape.
Such an ominous projection added another layer of urgency to the scientists' work here. As global sea level rises, would even more of Bangladesh be underwater? A key to this critical question was the Ganges River. At one time, the river flowed south through what is now Kolkata, India, carrying its great load of Himalayan sediment to the coastal part of the Ganges-Brahmaputra Delta, the Sundarbans. But in the 1600s, something happened. The Ganges completely changed course, heading southeast to what is now Bangladesh. It left behind a river channel, But the river in that channel was now called the Hooghly River. What was the impact on the delta? And why did the river's course change? Did earthquakes play a role? To take a look at what used to be the Ganges, Humayun Akhtar and Mike Steckler came to Kolkata from Bangladesh.
This is the Hooghly River flowing through Calcutta, and this used to be the main channel of the Ganges, but starting in the 1600s, this started to silt up and the river shifted and now flows to the east through Bangladesh.
When the Ganges River turned east, it no longer dropped its great load of sediment on the Indian side of the Sundarbans.
When it enters Bangladesh,
This was a concern to scientists. To investigate further, Humayun and Mike traveled down from Kolkata to make their way deep into the Sundarbans. Mike had been working in the Bangladesh Sundarbans, where the Ganges now flows and deposits its Himalayan sediments. He was eager to see how the Indian side compared.
Yeah, we're making a big loop.
It soon became obvious and unsettling.
It's not receiving enough sediments, and we're seeing a lot more erosion and land loss. And all along, as we've traveled along these banks, we keep on seeing erosion of the banks, but very little evidence of new land growing.
Overall, scientists have measured a steady drop in the level of the land's surface here, up to 4 millimeters per year. This means that if global sea level keeps rising, it will likely bring more flooding than usual. That could cause problems for this area's agriculturally based way of life. It was a different story over in the Bangladesh part of the Sundarbans.
What about this one?
Using compaction meters, GPS, and other means to measure the rise and fall of the land's surface, the scientists found that this land was actually being protected by the mighty Himalayan rivers that feed it.
There's roughly 1 billion tons of sediment delivered by the river each year that has built the landscape. So there's opportunity for the river and the delta to continue grading and maintain this landscape even in the face of more rapid sea level rise.
That was good news, at least for this particular part of Bangladesh. But the other side to this story was growing more ominous. Geologists were still struggling to see below the sediments where the faults were. But their data was starting to hint that the sediments were being warped by movements of the plates below, with profound consequences for the way water moves through the entire delta. Could this be the reason that even a mighty river like the Ganges changed course?
If we see a hillside here and a hillside,
Steve Goodbread's group tried a novel way to look for clues. It involved using local tube well drilling methods. Originally developed to obtain drinking water, this drill can drill down as deep as 100 meters, more than 300 feet, in one day, and extract samples of sediment.
Pretty dirty, weathered sand.
Now, this technology for installing drinking wells is the same technology we can use to get the layers of sediment that lie below us. And we catch those sediments as they come out of the pipe. And what we're looking at in those sediments is to understand how those layers of sediment are stacked on top of one another.
So do you think this stuff may come in?
From the sediments, Steve and his team found out, in greater detail than ever before, what the rivers had been doing.
As rivers migrate across the landscape, you get sands near the river channel, you get muddy sediments and a lot of organic matter preserved out in the floodplains where there's forests and swamps. So it's the types of sediments that are laid down at these different times and in different places in the delta that tell us this history of how the rivers, sea level rise, and tectonic deformation have all interacted to construct the landscape we have here.
Actually, we haven't run any strontium yet today, have we?
Drilling data confirmed that plate tectonic forces deep below did have a greater influence on the surface than was previously thought.
Yeah, that's good.
In some places, the sediments were very likely warped and deformed by past earthquake activity. Plotting the actual location of faults seemed within reach.
What's the interval you have taken?
5 meters.
To expand on the drilling data, Humayun, Mike and their group measured the electrical resistivity of the sediments below. This involved putting high voltage electricity between a long string of electrodes. The result was something like a CAT scan of the Earth's sediment layers. This method also showed warping of the sediments. The idea that tectonics were disrupting the surface gained traction.
This is the nucleus of the civilization.
As it did, the curtain began to lift on mysterious events far back in ancient history. This archaeological site is called Wadi Bateshwar.
Oh, look at this.
Thousands of years ago, it was an important city, a vibrant trading partner of ancient Rome. But the mighty Brahmaputra River changed course after the 7th century, and the city, no longer a major port, declined.
We can move now?
Okay,
we can move. Okay.
Were earthquakes behind this? With their new perspective, scientists suspected so.
You see the boulders in the pit underneath. I mean, they're just huge.
One of the most crucial historical events that the scientists studied was the devastating 8.3 Assam megaquake of 1897.
Right.
And then the river has just cut across this formation.
It struck close to what is now the Bangladesh border with India. But for some time, geologists had not been exactly sure where the fault was. Mike Steckler and Dhaka University students Nafisa Shamim and Moshoor Rahman were taking measurements at the Bangladesh border, near where the megaquake struck.
That's basically east-west.
It was here that Mike's group had made an important, but worrisome, new finding about the fault, the Dauki fault.
So the people used to think the Dauki fault was at the foot of the mountain, and now what we found is, in fact, it's farther in front but buried underneath the delta sediments.
We are moving towards the older rocks.
And we can see that through seismology, through our GPS array. So we're learning more about how these faults work when they're buried with sediments of the delta.
This new finding put the buried fault closer to Dhaka and the 16 million people who live in and around it. A large earthquake here will put many more people at risk than was previously thought. After pinpointing the Dauki fault, the scientists expanded their investigation to a broader area.
It slipped along this plane.
Now they realized that they might be unearthing a seismic threat greater than any they'd discovered so far. They worked to the east and south of Dhaka, directly above the area where the Indian and Asian plates collide to form the Burma Arc subduction zone. The scientists were uncomfortably aware that this was one of the most densely populated places on Earth, home to some 150 million people. People here had not experienced a large earthquake in living memory, but farther south they had. In 2004, the Indian Ocean earthquake, a magnitude 9.1, and a huge tsunami struck off the coast of Indonesia, killing 230,000 people in 14 countries. The earthquake ruptured the same plate boundary between India and Asia as the Burma Arc, only further south. It's called the Sunda megathrust. This part of the plate collision is under the Indian Ocean and can only be studied from ships. Scientists aboard the research vessel Falkor and other ships mapped this extremely dangerous underwater fault in detail. It was once thought that the geometry of the fault prevented it from producing a megaquake. But the Indian Ocean earthquake put that theory to rest. Because of the Indian Ocean earthquake, this part of the India-Asia plate collision had become relatively well understood.
We have the megathrust fault that reaches around here.
This was not the case for the same plate boundary to the north, where scientists were just beginning to turn their sights on the Burma Arc, which lies under Myanmar, Bangladesh, and northeastern India. Built directly over the Burma Arc is the city of Aizawl. It's the capital of the state of Mizoram in northeastern India. With a metropolitan population of 1 million people, this vibrant city sits on top of steep mountain ridges. Major earthquakes have struck here, but the last one was 250 years ago.
We know from history there's been a lot of destructive earthquakes in this area. And in the recent few tens of years, we haven't had a big earthquake. So people in this area, they don't have earthquakes as a big thing in their history.
Structural geologist Nano Sieber has studied earthquake zones all around the world, from Haiti to Italy.
The ripple marks, so the ripple marks lock, you can't have flexural slip.
Concerned by the threat of big earthquakes in this region, he came to work here with colleagues from India, Bangladesh, and the US. The geologic structure coming into focus below Bangladesh seemed to be extending beneath northeastern India too.
You can trace it back down here.
If confirmed, it was far bigger than anyone had previously thought, and potentially very dangerous.
The root of the system is going to be this huge megathrust, where the subducting plate goes down and the sediment on top are remaining on the surface. So that's the type of fault that produces the largest known earthquakes.
You know, this is obviously affected because
scientists urgently mapped out what they were calling the Burma Arc megathrust. It started to look like a massive, very low-angle megathrust fault, like the main Himalayan thrust fault, but wider, one of the widest faults on the planet.
The megathrust, it's huge. It's a huge area that can rupture, if indeed it's stuck or is locked, we say. And so that's the question. Is it locked or not?
The problem here in Mizoram, as in Bangladesh, was that the megathrust was deeply buried under sediments from the Himalaya. Only here, the sediments hardened into rock for millions of years and were folded and raised into rugged mountains.
So the fault, we say, is blind. It's not coming to the surface. So nobody has seen it.
Yeah, I'm thinking of larger.
Finally, using data from field mapping, GPS, and seismic networks, the scientists were able to see the blind fault. It was a gigantic section of the Burma Arc megathrust, and it was indeed locked and building up stress. At one end of that major seismic gap was Aizawl, and at the other was Dhaka.
The distribution of strain is telling us that at least the frontal part, you know, which you're talking 200 kilometers of this fault, is in fact locked.
If it is a bedding thrust,
it means that in the future you can have a huge earthquake.
A megaquake could come at any time, on the Burma Arc or on the main Himalayan thrust fault. Now the question is, what can people do to prepare? Throughout the region, construction methods are a great concern in the face of a coming earthquake. In Mizoram, how buildings are designed can be a problem.
Only a few generations ago, most of these people here in this part of the world lived in bamboo huts, which is very good because in this relatively hot climate, you want a lot of air, so you want to be off the ground and where there's snakes and there's insects.
But the design does not translate well to today's building materials.
They kept this design, which is not very good for earthquakes when you build by concrete and heavy bricks and heavy roofs.
In Aizawl, scientists and engineers have begun to push for building codes and construction methods that address earthquake safety. This is especially important here, where the danger from a big earthquake is compounded by the already chronic problem of landslides on the steep slopes. A big earthquake could trigger landslides in many places. Afterwards, it would be very difficult to receive help from the outside world. This landslide, caused by the monsoon, shut down the main road to Aizawl's airport for months. All traffic was diverted onto rough and rutted side roads. At the other end of the Burma Arc seismic gap, in Dhaka, earthquake building codes were put in place in the 1990s. But scientists and engineers warn that the codes are not adequate for withstanding large earthquakes. They want the codes to be modernized and enforced. Other safety measures in the region are in motion or planned. One of the first lines of defense is to upgrade schools. Some 5,000 schools were destroyed in the Gorkha earthquake of 2015. Luckily, the earthquake hit on a weekend when children were not inside those schools. But after the earthquake, many students had to attend school in temporary structures. Several hundred schools survived the Gorkha earthquake intact, like this one in Kathmandu. This school, like the others that survived, had been strengthened or retrofitted before the earthquake to withstand earthquake shaking. Nepal's cities and large towns have had building codes for new construction since 2005. Engineers found that these codes helped reduce the devastation wrought by the Gorkha earthquake. Progress is also being made in neighboring Bhutan. Since the late 1990s, building codes have required new buildings in some areas, like the capital Thimphu, to be earthquake resistant. But older buildings and rammed earth structures remain vulnerable to shaking from a major earthquake, and retrofitting is expensive. In Bhutan, a novel stopgap measure has been engineered to save the lives of school children. School officials are installing special new earthquake desks as a temporary measure. These super strong desks can protect children from falling debris during a big earthquake, unlike standard desks, which cannot. But scientists point out that this measure is only temporary. They say that by far the best way to protect children and everyone else is to retrofit critical older buildings and to build new buildings strong enough to stand up to earthquakes. The expertise already exists. It remains to be seen how much safer people will be when the next earthquake strikes. Unseen but not unfelt, powerful natural forces inside the earth are an integral part of life for the people of the Himalaya, and for the billions of others whose lands are connected to it geologically. The rise of the Great Himalayan Range has brought with it the serious difficulties of earthquakes, landslides, and flooding. But the mountains have also brought rain and great rivers, and our planet's most productive piece of life-sustaining land. Scientists are steadily unlocking the secrets of this active tectonic collision zone where so many of the world's people live.
We're in a syncline.
We're in the core.
These scientific findings are the first crucial step in diminishing the danger the next time Earth's great plates suddenly wake up, as they have done repeatedly in the past and will surely do again and again in the future.
We had earthquakes, and we all have earthquakes in the future as well. There is tremendously huge force which is all the time here in the Himalaya, and we should do everything understanding the force of the nature, force of the Himalaya.